This is a demonstration of how to use Stata to replicate the results of the regression analysis example in the statistics textbook by Joseph Hare and others. I used the 7th edition when cross-referencing my results to the book. I am aware that there are at least 3 different regional versions of this edition. These will likely have different page numbers, but as far as I can see, the example itself is the same across the different editions. The book is widely used by university researchers and students, but what may not be as well known is that you can use your preferred stats software package to try to replicate all of the examples in the book using sample data made freely available by the authors. I'll put a link down in the description to assist you with finding the relevant spreadsheet as well as other resources. This video is on the multiple regression analysis example in the second part of chapter 4. The regression is applied to the so-called HBAT sample data downloaded from the author's website. We use the variables x6 through x18 as candidate independent variables and x19 as the dependent variable. The sample size is 100 cases as set out on the first tab of the spreadsheet. Before we begin with the analysis, some disclaimers. As will quickly become obvious, I am a generalist, not a statistician. I also assume that you are reasonably familiar with Stata, such that you know how to import data, enter commands, save your results, and search for new functions wherever necessary. Another assumption I make is that you know how to deal with number formatting issues in Windows or Mac OS. This especially occurs if you live in a country, as I do, where a comma is used as a decimal point and a space as the thousand separator. This is the reason that I ran the Stata describe command immediately after importing the HBAT data to check that I have the correct float storage type. If you instead have string variables, you know that you have a problem with your settings and your regression attempt will fail at the first step. We now begin with the regression. Hare and co-authors apply what they call a stepwise estimation approach to selecting the independent variables. Each new variable is added to the model on the basis of it being the best out of those not yet included. Furthermore, if the addition of a new independent variable causes one previously included to lose its statistical significance, then the older one is dropped from the model. Therefore, the Hare approach is a hybrid mix of forward and backward selection. The first independent variable is the one that has the highest pairwise correlation, whether positive or negative, with the dependent. Therefore, we begin by calculating the correlation matrix using the option *0.05 to label all correlations that are significant at the 5% level. This replicates table 7 in the textbook. X9 is identified as having the highest correlation and so is the first independent variable added to the regression. The command is regress, followed by the dependent variable, which is x19, and then the independence, with x9 being the only one at this stage. The option beta is used with the regress command so as to replicate the standardized coefficients also reported in the book. For completeness, correlations and the variance inflation factor, or VIF, are also calculated, even though with only one independent, these quantities are somewhat redundant. This replicates the upper half of table 8. We observe that the coefficient of x9 is significant at the 0.000 level, and so this variable is retained at this point in the stepwise estimation process. Then we need to identify the next candidate independent variable. This is the one that has the highest significant partial correlation with the dependent, controlling for the independent variable that has already been included in the model. Therefore, we generate a partial correlation matrix using the appropriate Stata command in combination with the SIG option so as to obtain the p-values for each pairwise partial correlation. If you get an error code when trying to run this command, it will be because it is not yet installed on your version of the software. This replicates the central two columns of the lower panel of Table 8. These contain the decision-critical information for selecting the next candidate variable. The highest significant partial correlation is x6 at 0.532. The other quantities in the lower panel of Table 8 are not directly relevant to the selection of the next independent variable. Hare and his co-authors use them for discussion, not decision-making. However, if you would like to generate them, they may, with some repetitive effort, be replicated in Stata on a line-by-line basis as follows, using x18 as an example. Returning to the stepwise estimation of our model, we add x6 to the regression. To replicate as much as possible of the upper panel of Table 9, we also generate the correlation and partial correlation coefficients as well as the VIF quantities. Inspecting the coefficients of the two independent variables so far included in the regression model, we see that both are significant at the 0.000 level. Also, multicollinearity is low for both variables, with the reciprocal of VIF referred to as tolerance at 0.989. Hare and co-authors suggest a minimum tolerance level of 0.1, equivalent to a maximum VIF of 10. We next evaluate the adjusted R-squared and note that the addition of x6 has increased this indicator from 0.357 to 0.535. We therefore conclude that both x6 and x9 should be retained for the time being. To identify the next independent variable, we now need the partial correlations of the excluded variables controlling for x6 and x9. We inspect the matrix and establish that the highest significant partial correlation of the excluded variables is x12 at 0.676. So we add x12 and run the regression with 3 independent variables, followed by the commands required to generate the other quantities reported in the upper panel of Table 10. We observe that the coefficients of all 3 included independent variables are significant at the 0.000 level. Multicollinearity remains acceptably low for all variables, with tolerance above 0.9 in each case. The adjusted R-squared has increased once again to 0.745. Therefore, x6, x9, and x12 are kept in the model at this stage of the stepwise estimation, and we proceed to generate the partial correlation matrix controlling for all 3 of these variables. This indicates that x7 should be added next. Although only one independent variable at a time should be added to the model, Hare and co-authors save paper and ink by including both x7 and x11 in a single step. The regression is now run with 5 independent variables, followed by the calculation of the correlations, partial correlations, and tolerances of the included variables so as to replicate the quantities reported in the upper panel of Table 11. We observe that the coefficients of all 5 independent variables are significant at the 0.5% level or lower. Multicollinearity has increased, but the lowest tolerance is x12 at 0.347, which is above the suggested minimum tolerance level of 0.1. The adjusted R squared has increased from 0.745 to 0.763 with the inclusion of x7 not shown as a result of the combined steps, and then to 0.78. Therefore, all 5 independent variables are retained. The partial correlations of the excluded independent variables are now calculated. None of the remaining variables has a significant partial correlation, with the lowest significance being x16 at 8.8%. Therefore, no further independent variables are added to the model, which is provisionally finalized. In summary, we note that the F statistic indicates that the overall model is significant at the 0.000 level. In addition, the R squared shows that the 5 included independent variables explain 79% of the variability in the dependent variable. Furthermore, at each step of the process, the adjusted R squared consistently increased each time. That concludes the objective of this demonstration. However, the regression process is not yet complete. The model must, for example, still be evaluated against the assumptions of linearity, constant variance, independence, and normality. These issues are discussed in detail in the textbook. If you thought this video was helpful, then please consider giving it a thumbs up and subscribing to the channel. If you have a question, leave it in the comments section. I do my best to respond to all messages.